Okay, today let's talk about circles. Okay, so circle. We all know what a circle looks like. Circle has a center. O usually is called a center. Every point on the circle P, the distance between this center and this point, the distance is a fixed. We use this symbol to represent the distance. The distance is a fixed number. This fixed number, we call it radius. Okay, so the circle is a collection of all points P such that the distance OP is a fixed number. And if you connect between the center and any point on the circle, this represents a radius. The radius usually we use R to represent. Okay, and when you have a circle, if you get a segment from one point through the center, reach the second point on the circle, this is called the diameter. So diameter is a segment from one point to the another point through the center. So diameter, you see here, diameter, here is a radius, here is a radius. The diameter is a twice of the radius. Diameter is a twice of the radius. And also you can see that for any other case, if you have 2 points, you connect those 2 points. This is called a chord, chord, C-H-O-R-D. And the chord has some length. Diameter is the longest chord. Any other chord should be shorter. If it's not diameter, it should be shorter than the diameter. So chord is shorter than diameter. And when you have this circle, start from the center, you get 2 radius. These 2 radius give us 2 regions. You have this big region, you have small region. They are both called sectors. So here you have a sector 1, here you have a sector 2. 2 sectors. Sector is between 2 radius. It's a sector. Sector 1, sector 2. Okay, and on the circle, you just trace the point on the circle. Then this from one endpoint to another endpoint. This is called an arc. It's called an arc. So the arc, if you get the complete circle, you cover the complete circle. This is called circumference. The circumference, perimeter, the circumference. So that's the basic names for the circles. And when you have a circle, you get another line touching the circle. Touching, we mean there's only one intersection point. When there's a line touching the circle, we call the tangent line. So a tangent line is like you have a line, you move it until the line touches the circle. Then this is called a tangent line. Okay, and if you keep moving this line, the line will intersect the circle at 2 points. Here, there's only one intersection point. If the line intersects the circle at 2 points, then this line is called a secant line. a secant line. A secant line will intersect the circle or curve at more than one point. Here you have 2 points. So here is tangent, and once you move past that limit position, it becomes a secant line. And the secant line, you slightly move it, it is still a secant line. Okay, so from the circle we have center, radius, diameter, chord, sector, arc, circumference, tangent line, and secant line. Okay, so we have those concepts. Okay. Okay, now let's see. In the circle, we use two radius to form an angle. Two radius to form an angle. This angle is theta is called a central angle. Okay, a central angle. A central angle means its vertex is the origin. And its two sides are radius. Okay, so that's a central angle, a central angle. For the central angle, if we modify it a little bit, so we do not use a radius, we use two chord. You see, this is one chord, this is another chord, two chord. If you have two chord, those two chord intersect at the circle, not inside, not outside, on the circle. If this happens, this theta is called an inscribed angle. An inscribed ed. This is inscribed inscribed circle angle. Sorry, inscribed angle. Okay, and from here we are going to study the relation between the central angle and the inscribed angle. We will see some relations. Here is the stuff we're talking about. So what is the setting? The setting is the following. You first fix 2 points, and you get the center. You form two radius. You get the central angle. This is called the central angle. We call it theta. Okay, and then we use dotted line. Let's say we use a red line. This we have alpha. Alpha, this is an inscribed angle. So alpha is an inscribed angle, and theta is a central angle. The relation between alpha and the theta is that alpha, theta share the same arc. So this arc faces the central angle theta. It also faces the inscribed angle alpha. So when we have this setting, we claim the central angle is always twice of the inscribed angle. Okay, so for the same arc, its central angle is twice of the corresponding inscribed angle. So that's the relation between the center and inscribed. Okay? So let's see how do we prove it. So this is a theorem. We're going to prove it. How do we prove it? Let's make it bigger and so that we can see the picture clearly. It's difficult to draw a better circle. Okay, this is theta. Remember, we call it theta. And okay, this is alpha. Okay, in order to show theta is 2 times alpha, we first connect the vertex of alpha with the center. We get the radius. Let's get the name for those points. So this is center. We call it O. This point we call it A. This point we call it B, and this point on the circle we call it C. Okay, and then let's say we call this angle alpha, this angle 1, this angle 2. Okay, so the left half angle, not half, left angle we call it angle 1. The right angle we call it angle 2. So we know that what? We know alpha is angle 1 plus angle 2. Okay, so this is you just divide the alpha into 2 parts. And then you see what? You see this OAC. This OAC. This is an isosceles triangle. Isosceles triangle. What is isosceles? How do I spell isosceles? Isosceles triangle. Yes, isosceles. SC. So SC. Isosceles triangle means because OA is equal to OC, they are both the radius. Okay, OA, OC, they're both radius. So of course they equal to each other. They equal to each other, then this is a isosceles triangle. And here let's extend this radius a little bit long. Okay, isosceles triangle, we know that. From isosceles triangle, here, this angle, we call it angle 1. Then this angle is also angle 1. Here's 1, because this side is equal to this side. And remember, we extended this radius a little bit. Then the theta is also divided in 2 parts. So we call this part angle 3 and this part angle 4. So let's put it here. Theta is angle 3 plus angle 4. Okay, so this is the external angle for the triangle OAC. So angle 3 is sum of angle 1 plus angle 1. It's twice of angle 1. So here we use a property. What property we have? Assume we have a triangle. You have angle A, angle B, angle C, and here you have an external angle D. External, it's not internal angle, external angle D. Then angle D is always equal to angle A plus angle B. This is the basic property from the triangle, because angle D plus C is 180 degree. ABC together is 180 degrees. So D is always equal to angle A plus angle B, the other 2 angles. So here, 3, the other 2 angles will be 1, 1. So it's twice of angle 1. We only study the left half, left triangle, and we have the right sharp triangle. So the triangle OBC is an isosceles triangle also with the same reason. You have 2 radius. OB is OC. So this angle is 2, this angle is also 2. And angle 4 is external. Then angle 4 is angle 2 plus angle 2. It's twice of angle 2. Okay? Okay, so let's summarize. Theta is angle 3 plus angle 4. Angle 3 is twice of angle 1. Angle 4 is twice of angle 2. You factor out 2, 2, you get angle 1 plus angle 2 and times 2. Angle 1 plus angle 2 is alpha. So it's theta is equal to 2 alpha. So we finished the proof. We prove that for the same arc, its corresponding central angle is twice of the corresponding inscribed angle. Okay? It's twice of a corresponding inscribed angle. So that's the finish. And this theorem has a very interesting corollary. What is interesting corollary? If you have a circle and you fix an arc, for example, this is arc AB, then you just randomly pick up the chord with the same arc AB. This angle, angle 1, angle 2, whatever way you form the angle, angle 3, angle 4, all these angles, angle 1 is equal to angle 2 is equal to angle 3 is equal to angle 4. It doesn't matter how you construct. Once you fix this arc, then the facing inscribed angle will be the constant. Why? Because they are all the half of the central angle. This inscribed angle is not unique, but the central angle is unique. Central angle is always double of them. Central angle, if you have the central angle here. The central angle, this is central angle, fixed. It's twice of 1, it's twice of 2, it's twice of 3, and twice of angle 4. So angle 1, 2, 3, 4 are always the same thing. So once you fix this arc, you just form the inscribed angle. You cannot get different angle, just the one angle. So this is the relation between the central angle and the inscribed angle. Okay, so we have central and inscribed. Okay, then let's see next. When you have a chord, chord, it can be any direction. So let's just rotate it, because the circle, you can rotate it so that the chord is horizontal. If it's here, if it's not horizontal, you rotate it and make it horizontal. If you have a horizontal chord, check here. You start from the center. You form the orthogonal line, perpendicular line. Form the perpendicular line. Okay, we are going to say this line is a bisector. It's a bisector, perpendicular bisector. This radius is the perpendicular bisector. Let's call it A, B, and O of the chord AB. Why it is a perpendicular? We make it perpendicular. Why it is a bisector? Let's try it. Here and here. Okay. When we have this right triangle, you have this angle and this side. This is a shared side. Here's the right triangle, here's the right triangle also. You have the shared side, the same radius, the same hypotenuse. So for the right triangle, you know two sides. The third side will be the same thing because of the Pythagorean theorem. So remember, assume we call this as B. This height we call it B. This part is a, this part is also a, must be also a, because a squared plus b squared is r squared. A squared plus b squared is r squared. So it's controlled by the Pythagorean theorem. So this a is equal to this a. So that's why it is a bisector. Okay, so for arbitrary chord, if you draw the perpendicular line through the origin, through the center, perpendicular line through the center, then this perpendicular line is also the perpendicular bisector. Okay, so it's a very symmetric. And then if you get the second chord parallel to it, we can conclude that this arc, the left arc, is equal to the right arc. The left arc is equal to the right arc because you do have a symmetric shape. You have the symmetric, pure symmetric shape. So those two arcs are the same. Okay, so just keep this in mind. If you have two parallel chords for arbitrary position, for example, you get chord here and chord here, parallel. Those two chords are parallel. Then the two arcs between these two parallel curves are equal. They are equal. Okay, so this is the property we are going to use. Okay, so now let's see. We already formed the central angle and the inscribed angle. The thing is that for the inscribed angle, we must require the intersection, or the intersection of two chords is at the circle. But sometimes when you have two chords, they intersect possibly inside the circle, not on the circle. Okay, when they intersect inside the circle, they form an angle alpha. Then what is the relation between the arc, those two arcs? Now you have two arcs and the alpha. Okay, so how do we describe the relation between them? Let's say this is arc 1, ARC1. This is arc ARC2. So how do we do it? We first start from this arc 2 and draw the parallel chord. So we get the parallel chord. Once we get a parallel chord, remember we just had this experience. Those two chords are parallel. Now this arc 2 is equal to this arc 2. We have to move those two arcs together. Let's put prime, arc 2 prime. Arc 2 is equal to arc 2 prime. Okay, then you see this is a parallel line. These two are parallel line. This alpha is equal to this alpha. Okay, so now this alpha is an inscribed alpha. Let's call it alpha prime. Inscribed angle. Okay, so for this inscribed angle, it is half of the central angle. If arc 1 and arc 2 face central angles theta 1 and theta 2, so whenever you have an arc, you have the central angle. If arc 1 and arc 2 face a central angle theta 1 and theta 2, then alpha is equal to 1/2 theta 1 plus theta 2. Because here you move this arc 2 to this arc 2 prime, then you add those two arcs together. They are connected. You can add them. Add them, the central angle will be added together. because you have angle, the center is here. This is the central angle facing to arc 1. This is central angle facing to arc 2. So you add them together. This is a central angle facing the total arc 1 and arc 2. And this alpha is going to be the half of the sum. So alpha is a half of the sum of the central angle. Okay? So that's the relation. For example, if we let's say if this arc faces an angle, let's say 140 degrees, this arc faces angle 60 degrees. We just say assume. We don't measure. Then this angle is going to be 1/2 140 plus 60. This must be the central angle. It must be the central angle. Like you find the center, you form it. Okay? So it is a 1/2 times 200 degrees. It's a 100 degrees. Okay? It's not that precise, but we just demonstrate. So once you know the central angle for the corresponding arc, you add them together and divide by 2. So this is this is called an internal angle formed by 2 chords. Okay, internal angle formed by 2 chords. Okay? So the internal angle is half of the sum of 2 central angles. So internal angle is formed when those 2 chords intersect inside the circle. If those 2 chords intersect outside of the circle. Okay, inside, internal, outside, external, on the circle, inscribed. Okay, so this is a external. This angle is called the external angle. Outside. Internal, inscribed, outside, external. Okay, this external angle again has 2 corresponding arc. Here you have arc 1. Here you have arc 2. And of course, one is bigger and one is smaller. Arc 1 and arc 2. Now, arc 1, arc 2 both have the corresponding central angle. Theta 1 and theta 2. Okay, so here, because of this setting, we see here theta 2, arc 2 is longer than arc 1. Theta 2 is greater than theta 1. The longer arc has a bigger internal central angle. Okay. Okay. Then what let's call this inscribed external angle alpha. Now what is the relation between alpha and theta 1, theta 2? What is the relation between alpha, theta 1, theta 2? We do the similar thing. We start from one endpoint of this arc 1. We draw the parallel arc. It's a parallel line. So this alpha can be moved to this part. And now this alpha prime. Now this alpha prime is an inscribed angle. Alpha prime is inscribed. It's inscribed angle. Then it faces the arc. This is not arc 2. Here, this part is equal to arc 1. So this this piece is arc 2 minus arc 1, arc 2 minus arc 1. Okay, so top, this part is arc 2. This is arc 2 minus arc 1. Okay, then alpha prime faces arc 2 minus alpha 1. It's an inscribed angle, so alpha is 1/2 theta 2 minus theta 1 is half of the difference. External angle is half of the difference. Internal angle is a half of the sum. Okay, so we have central angle, internal angle, inscribed angle, external angle. Okay. Okay, very good. Okay. Now let's see another thing. We talk about angles. After we talk about angles, let's see one application of this angle stuff. Let's assume we have a diameter. We have diameter, horizontal diameter. Diameter, this is a half. The bottom is a half of the circle. Diameter divides the circle equally into two parts. This half of the circle faces the central angle 180 degrees. So the central angle is 180. This is 180. That is 180. The total is 360. Okay? So the central angle is 180. Then the inscribed angle will be half of the 180 is 90 degrees. Okay? So the inscribed angle will be half of 180 is 90 degrees. So this gave us an observation. The diameter always gives the right inscribed angle. So the diameter always faces 90-degree inscribed angle because its hypotenuse is 180. Okay, so it's always a right triangle when you do this sketch. It doesn't matter where you choose this vertex. This is a right triangle. If you put it here, if our sketch is precise, this is also the right angle. In whatever position you draw it, it's always a right triangle. Okay, that's the property. Now we are going to use this property to show some algebraic inequality. Arithmetic sequence is greater than or equal. Arithmetic mean average is greater than or equal to the geometric average. Okay, so arithmetic. Okay. So what is the arithmetic mean? So when you have two positive numbers, a, b, positive, then a plus b divided by 2 is called the arithmetic average, or arithmetic mean, average mean of a and b. Okay, a plus b divided by 2. And square root of a times b takes square root is called the geometric average of a and b. So you have arithmetic average, you have a geometric average. And the result says the arithmetic average is always greater than or equal to the geometric average for any positive numbers. We only discuss positive number so far. Okay? So how do we prove it? By the circles we just described. Here is the case. Check here. We have A and B, they are positive, so they represent some segment. For example, this is A, and you continue draw it, you have B. So this is A and B. They may or may not be equal, it doesn't matter. Okay, and A and B together, we consider it as a diameter. So we find the center, a midpoint, and we draw the circle. So we draw a circle so that A plus B is a diameter. Okay, so we first get A extent, B distance, we get A plus B. And then we find the midpoint of this long segment and draw the circle. So you have the circle with a diameter A plus B. And you have this point. This is the center. This is A. Remember, always keep in mind, this is A. This is B. Okay, at this intersection point, we draw the vertical line. This is vertical. And this vertical line intersects the circle at some point. Here we call this A, we call this B, and this intersection point we call C. And we connected AC, and we connected BC. We connect AC and BC. From the previous discussion, we know that AB is a diameter. AB is a diameter. This is a 90 degree. The inscribed angle, the corresponding inscribed angle is 90 degree. Here, remember, we do the perpendicular line. So this is 90 degree. This is 90 degree. Okay. In this triangle, we have one right triangle, second right triangle. And these left and the right, these two small right triangles are similar. And this point, let's call it D. The small triangle is similar. Okay. For the similar triangles, so triangle ADC and the triangle CDB are similar. Why they are similar? You see here, they come from the same. You see, this is a right triangle, so this angle plus this angle is 90 degree. B plus A is 90 degree. And in this, okay, remember, let's check here. B plus A is 90 degree because this large ABC is the right triangle. Two acute angles, the sum of two acute angles is 90 degree. And for this right small triangle, B plus this angle, the top angle is, this is the right triangle, B plus this top angle is also 90 degree. So this angle is, plus B is 90. This A plus B is 90. So those two angles are the same. Here you have right angles. Right angle is similar, is equal to the right angle. So for the right triangle, if you have a pair of acute angles are equal, those two right triangles are similar. Okay, so we have similar triangles. Once we have similar triangles, we have the ratio equality. So AD is a longer side. So AD over CD. CD is the longer side, except the hypotenuse is the longer side of the right angle. Over CB is equal to what? AD over CB is equal to CB. It's a shorter side of the left angle over DB. It's a shorter side of the right angle. AD, read it. AD is A. CB, I don't know. So right side CB is CB. DB is B. Okay, so we have this triangle stuff and similar triangle stuff, and we get ratio. And then we do cross multiplication. So we get AB is equal to CB squared, CB times CB squared. So CB, we take square root, CB is square root of AB. So what is square root of AB? CB is, square root of AB is geometric average. So it means this height really give us the geometric average of A and B. Okay, so this is B. This height is. And what is a arithmetic average? Arithmetic average is A plus B divided by 2. A plus B is the diameter. We know that A plus B is a diameter. Then A plus B over 2 is the radius. A plus B over 2 is the radius. How do I draw the radius? Radius, we draw it through the center vertically. This is the radius. This is A plus B over 2. Okay, clearly, you see here, this height is shorter than the radius. CB is a height. It's shorter than the radius R. So the geometric average is less than or equal to the arithmetic average. So that's the proof. Okay, so this is a very interesting proof. It gave us a very good result. The arithmetic average is always greater than or equal to the geometric average. Okay, excellent constructive and the geometric proof for the algebraic representation, algebraic inequality. Okay. Okay, another example, another computation. For a circle, we randomly draw two chords that intersect at the point, let's call it a P. The P is just some point inside the circle. And let's give some name. So A, B, C, and D. Now you see here the chord with this intersection point has a four sub segment. So let's call it A. Here's A, here's B, here's C, here's D. Okay, so four parts A, B, C, D. Then the theorem says, you see this A and the C, they are from one chord. So A times C is equal to B and D are from one chord, is equal to B times D. Quantity. A, B, C, D are numbers. So A times C is equal to B times D. Okay? Why? Okay, let me draw it here and we show the proof. The proof is very short. So A, B, C, D. So first we connect A, B, and C, D. We'll connect A and B, C and D. At this point we call it P. Then we claim that the triangle ABP and the triangle DCP are similar. This triangle, they are similar. Why? Let's see. First, this is opposite triangle. Opposite angle. These two angles are the same. So let's call them angle 1. This is angle 1. This is angle 1. Opposite angles are always the same. Okay? And second, this angle B faces arc AD. Angle C also faces arc AD. Angle B, C face the same arc. Then angle B is equal to angle C. Whenever you see here, this is angle C, this is angle B. They both face angle AD, so they are equal. For the same arc, all the inscribed angles are equal. And same reason, angle A and angle D are equal, face the same arc. Then angle A is equal to angle D. Angle A, it faces BC. Angle D also faces BC. So you have two triangles. All three pairs of angles are equal. Then those two triangles are similar. For the similar triangles, the corresponding sides are proportional. So B faces A, C faces D. So B over C. AD are same. B faces A, C faces D. So B over C is equal to A faces B, D faces C. So it's equal to A over D. Okay, so the corresponding side. Okay, now let's do the cross multiplication. You see here, well, let's do cross multiplication. You do cross multiplication, you get BD is equal to AC. Right? So that's a very short and a quick proof. So when you have two chords, they intersect inside the circle, then you have 4 segments, and the product of 2 is equal to the product of the other 2. Okay, so this is an interesting property, and the next time we will continue this study and get even more complex result from this stuff. Okay, we finish this time. Thank you.